Lee-san presentation will begin shortly. The presentation time is 30 minutes. Please welcome Lee-san with a huge round of applause.
Okay. Good afternoon, everyone. Can you hear me clear? Okay. Today, I'd like to share my work about building a Python-like array backend. So the title is How Fast Can We Go? Build a NumPy-Like Backend in C++ with Python bindings. First, let me introduce who I am. My name is Kuan-Hsien. I'm from Taiwan, and I'm now a software engineer for embedded controller in CNC machine. And now I'm also contributing in open source in a community called SciWork in Taiwan. We are mainly focused on programming for sciences. And my project is called MarMesh, which is also the work for this talk. And here's the outline. I will first introduce the array element-wise arithmetic operation in both NumPy and Python and compare their performance. And then introduce our project. Then I'll introduce how I accelerate the array arithmetic operation. Okay, let's start it. First, we all know that NumPy has really fast performance for numeric program, but why? To answer this question, we have to first know about the object system in Python. All the Python objects are structures in C languages. So they all have the same header, which is called PyObject in the left-hand side, and it contains a reference count for garbage collection and a type information to identify which type it is. The information might contain like the type name and the size of the object and some member variable or member function, etc. For example, at the right-hand side, you can see there are two objects. One is pylong object, which is used for integers in Python. Aside from the PyObject header, there is a long value which stores the real value of the integer. And for the list, there might be some field for the size of the list so that we can use len function to get the number of items in the list, and then the actual buffer that stores the object list. And then there must be an allocation size to know that how much buffer that we have now, so that we don't get any memory errors. So that from this schematic, we can know that if we want to do any operation in Python, we need to first extract the value out from this structure, and then do the operation, then store them back to the object. So it can be relatively slow. And if we loop over the Python list, we have to know that the script of Python that will always first interpret into bytecode and dispatch and execute it. So for example, here, this is the simple list iteration. We can see the for statement is transferred into this kind of bytecode, and the addition is transferred to the other bytecodes. And these bytecodes have to dispatch in C functions and then just transfer into a bunch of assembly, so that this can be slower. And what about NumPy? In NumPy, all the data are stored in a C-level array instead of the PyObject array, so that they don't need to extract the value out from PyObject. They can just directly access the value. With this design, it is really well for element-wise operation, because it's more compact, it's more efficiency to go through every element-wisely, and then it can be optimized in instruction level. And so from the right-hand side, you can see this is the definition of a ND array. It contains a contiguous data buffer which stores the real value of those of the array. And then there are some metadata to describe the array. And the most important two are shape and stride. They are used to locate the elements of the array. So let's take a matrix, which is 3 by 4 of 32-bit integer, for example. Here you can see the right-hand side, there's a schematic of this matrix. And in the memory, there are actually stored in a contiguous memory block with the beginning marked as the data. And then each element occupied 4 bytes and etc. So the total buffer will stand for like 48 bytes. The 2 metadata here are stored to use for different usage. Shape is to represent the amount of element in each dimension. So here we know that in the first dimension, it contains only 3 elements. In the second, there are only 4 elements. And stride is to represent the offset of 2 adjacent elements in the array. So for example, if we want to go to the next element along the first dimension, we have to cross 16 bytes. And if we want to go to the next element along the second dimension, we have to go across 4 bytes, so that the stride will be recorded as 16 and 4. The unit is byte. With these metadata, we can simply get any element in the matrix using this formula, with A and B, with A less than 3 and B less than 4. Okay, with this metadata, we can easily reinterpret the data without actually move the data from one memory block to another. So for example, if we want to reinterpret this matrix to a 6x2 matrix, what should we do? We can just take the metadata here and then modify them. With this modification, the data is reinterpreted into a 6x2 matrix, so that we don't need to do a lot of buffer copy. We can just modify these values. Okay, with this knowledge, I'm start to make my own array. Our project, MarMesh, is a mesh calculator and visualizer that have to handle a large amount of data, so that what we want is speed. We want to be really fast. That's why we implemented it in a C++ library. While we want it to be also usable for users, so that we wrap it with a Python interface. And also, we make our array in a NumPy array compatible metadata, so that the buffer can be transferred from NumPy to ours or from ours to NumPy. The Python interface is created by a library called PyBind11. Because that Python can accept C or C++ dynamic library as an extension with those, if the dynamic library has a certain pattern of functions. And PyBind11 handles these works for us. So it first basically just wrap the C++ object into Python object by first generating the PyType object for our C++ object. So it will list the name of those functions for us into the PyType object, so that Python interpreter can know what is in our object. And then it handles the PyObject header for us, and also the reference count. And last, it casts the object from Python and C++. So for example, if there is a function call in Python, it will first extract our C++ object out from the PyObject. And then it calls the C++ function that we wrapped using the C++ object. And then after that, he will cast the return value back to Python object for further usage. Okay, and now I'm ready to tell you how I make the array arithmetic operation even faster. So here, I use some different technique to accelerate these operations. First, we start using loop with row pointer. And this is actually the way that NumPy implement the element-wise operation. But the performance here shows that it does not really good, and it's not even close to NumPy. So we try to introduce the SIMD, which is a hardware feature that can accelerate these kind of element-wise operation. And it works, but it's still not good enough. So then we reorder the data movement in our operation. And finally, it got even better and exceed NumPy. And these data here are the benchmark of an out-of-place addition on an array with 4 million elements. Oh, sorry, 2 arrays. So you can just imagine it as this statement. So there are 2 arrays adding together to become a result array. And of course, we do also subtraction, multiplication, and division. But because of the limitation of the space, I can only show you the result of addition. They all share the same trend. OK, let's dive into the detail. First, I would like to talk about benchmarking. To benchmark our code, it is really great to have the Python binding, because with Python, I can easily write a script for the benchmarking. I can basically just make a random array using NumPy and transfer the buffer to our array, and then call the profile arithmetic functions, then do all those post-processing in Python. So with Python, I don't need to care about those typing stuff in C++, and I can find error really very easily because I don't need to handle those memory errors in C++. That was really great. Then for the acceleration, we start here, loop with the row pointer. This is the NumPy style. Here you can see from the NumPy code, it is actually just a for loop that adds all the values in the second argument to the first argument of this function. And basically, see the right-hand side, there are just 2 pointers pointing to 2 arrays, and add one value to the another, and then loop to the next one, and do the same thing, get to the next one, and then loop through the whole buffer. That was the very beginning. And we found that it's not performs enough, so that we start to introduce hardware features. And here, we introduce first SIMD. It is an abbreviation of single instruction multiple data. So here, in the previous slide, the normal loop is actually work as following in the instruction level. We first have to load the value on both sides to registers, and then add them together, store them back to the memory, and then get to the next element, do the same thing, so on and so forth. With SIMD, what can we do? We can actually load multiple data into a specialized vector register that contains multiple data there, and with only one instruction, and then do the addition or subtraction, something like that, in also one instruction for element-wise addition, then store them back to the memory, and so on. So that after looping through the whole buffer, we can know that with SIMD, the instructions execute is actually way fewer than normal loop. That is how it speeds up. SIMD speed up with this kind of special register. And the level speeding up is actually depends on the data type. So that here, if we are performing operation on 16 bits values, it can perform 8 operations at the same time. And if we are dealing with 64 bits value, it can perform 2 operations at the same time. And after introducing SIMD, we got this kind of improvement. You can see in every data type, it got a really great performance improvement. Well, here, I would like to mention a small application tip that we should always inline every function in the loop, because that the function call actually incurs a lot of significant overheads, so that if with too many function calls, it will make the performance worse. So on the top of right-hand side, there is the example of the assembly that the functions are, the unnecessary function is made. So you have to get to the jump to another function, then maybe execute one instruction, then return back. So what we should do is that, like the right-hand side in the bottom, we should inline every instruction as much as possible in the loop, so that they don't need additional jump from the program flow. Otherwise, the performance might be even worse than just loop through the whole buffer. Okay, let's get back to SIMD performance. Here from the data, probably we found that there's a little bit strange thing, which is that I've said that if we are dealing with 8-bit values, theoretically it can get 16 times faster. But from the result, we only found it's about 2.3 times faster. What's wrong with this? After look into the assembly, I found that actually in the loop with row pointer, the compiler have already helped us optimize those code into SIMD instruction. So if I turn off the compiler optimization, it will make an even worse result. And you can see here, the -03 optimization option has already made 8-bit values 7 times faster than non-optimized code. So if we compare the non-optimized code with our SIMD implementation, it is actually close to the theoretical value of the speed up. So SIMD actually work. Finally, after those row pointer loop and SIMD introduced, and I reorder the data movement in our operation. So why we result in this? Because first, for memory locality, we divide the operation into 2 phases. The first phase is copying one operand to the result buffer. And in the second phase, I do the addition from the other operand to the result, so that only 2 buffers will be used in one phase. For example, in the copy phase, only one operand and the result will be used. And the add phase, the other operand and the result will be used, so that it should be good for memory locality. While the profiling result doesn't say that. The data copy actually works way more time than the calculation here. So we use another approach that we first do the addition from both operand to the vector register. And then we load the result directly into the uninitialized result buffer. With this approach, the performance gets better, even though they are not just as fast as the pure addition in the last slide. And now we are faster than NumPy. So here's the takeaway. First, I would like to say that Python and C++, they actually work together very well. It can accelerate not only the calculation or the critical runtime, but also accelerate the development, because I don't need to handle those complex errors. Then, the compiler that actually did a really great job for helping me make the row pointer get to 7 times faster. But handcrafted SIMD might possibly run faster, and it's worth a try. And third, we have to definitely look into the assembly to know that how to help our compiler to work better. Then later, I will try to analyze the cache, the instruction between those data movement, and maybe try to introduce some other features to make it even faster. That's all of my talk today. And then now I want to do some advertisement. As I mentioned, the community I'm now in, Cywork, we are holding a conference in Taiwan in the mid of December. And now we are calling for proposal. If anyone who is interested in giving a talk in programming for science is welcome to scan the QR code and submit your proposal. Thanks, everyone.
Thank you for your presentations. If anyone has any questions, you may ask.
So thanks for your presentation. I want to explore a bit about the performance beat the NumPy part. Do you explore the reason why? It's because NumPy rely on the compiler default optimization, and do you see any opportunity to make your solution be part of it?
Sorry, you say that NumPy depends on what?
The NumPy's performance is worse because it depends on the compiler's default optimization. Or what's other reason why your performance beat that, and can you make it part of the NumPy solution?
I think we can definitely. I didn't really look into how NumPy works like that, but I would say as I mentioned here, the NumPy implementation is that they use the compiler optimization to make their best, and with this code, so that I think their reason possibly might be that with this they don't need to really depend on each specific hardware, because if you want to introduce SIMD or some other features, you must dealing with different platform, different hardware to check whether it is support these features. And it definitely worth to do some more research on how NumPy does it, but I haven't done that yet.
Yeah, how about my second question? Do you consider put your solution be part of the feature in NumPy?
There will be a possibility, but I think I can still try other ways that might possibly fit the NumPy, possibly fit how they want to do. For example, as I mentioned, maybe they don't want to introduce these kind of hardware-specific features. So other part or other compiler optimization might be better way to do the contribution to NumPy. Thank you.
Any other queries?
Thank you for your talk. I was just wondering, have you done any benchmarks with polars along with NumPy by any chance? I'm sort of curious about how Rust would compare to C++ implementation and your optimizations.
Oh, sorry. You say benchmark on polls?
Polars, yeah.
Sorry, I haven't heard of that
okay.
library.
Sorry.
Is it a library on Rust or?
Yeah, it's written in Rust and it's like a NumPy out.
Oh, I wasn't do that before. Sorry for that.
Okay, no problem. Thank you.
Thank you so much for your presentations. Everyone, please give a huge round of applause for the speakers.